In this video we're going to look at line shapes, backgrounds and how peak models are managed within CasaXPS, and we'll also have a look at Monte Carlo simulation as a means of testing a peak model. The data we'll use in this video are from polymethyl methacrylate, and this provides us with two nice examples for peak fitting. The carbon 1s consists of a set of chemically shifted components. So we have potentially 4 different chemical states for the carbon, and they all have different binding energies. And we also have oxygen 1s, and there are only 2 peaks, so we should see 2 equally sized peaks, and these are chemically shifted so that we can actually see these peaks, but not too shifted, so we have a relatively narrow interval over which the oxygen 1s is located. This means that we can see the background, and the background that is associated with the carbon 1s is slightly more involved because the changes in the background may occur at some point beneath these carbon peaks. The data file, or the VAMAS file that contains the PMMA data, is loaded via the Open VAMAS File dialog window. When I select the file opens, and in this case we can see how the display state has been resurrected using a file that is also within that directory. That's visible if we use the Convert to VAMAS File dialog window, because it shows more than just VAMAS files, and we can see that associated with this particular VAMAS file there's a .sff file, and this is a display state file that was saved when this VAMAS file was saved, and will be read if you open the file using the Open VAMAS File dialog window. I illustrated the way a display state could be saved, so I could display the data in a form that matched this diagram here for polymethyl methacrylate. I've color coded these carbon peaks, and you can see in this spectrum that's fitted with 4 different components that these components are similarly color coded. So you can see that the hydrogen carbon bonded carbon, and here we see there are 2 of them, and so we have a peak that's twice the size of these other peaks, and that's because there are only 1 in each one of these chemical states, where we've got carbon that is bonded to carbon that's double bonded to oxygen, and this has produced a small shift. When we have carbon single bonded to oxygen and hydrogen, we produce a larger shift, but the largest shift occurs when we have carbon double bonded to oxygen and also single bonded to oxygen. So we have a significant shift here in this peak. Now it's worth pointing out that when you look at the oxygen, these 2 different chemical states for oxygen produce a binding energy that is in the reverse order to the one that you see in the carbon 1s. So this is the double bond, and this is the single bond when viewed as oxygen 1s, whereas this is the single bond and this is the double bond in carbon 1s. These peak models were created using the quantification parameters dialog window, and on this window there are 2 property pages that correspond to regions and components. The regions define an interval over which a background is defined, and the components property page lists a set of parameters that are used to define these components. So in order to illustrate how these 2 property pages are used, we'll go back to the original data and we'll load the data file before any processing has been performed. The data file consists of a set of measurements that were all measured from the same polymethyl methacrylate sample. So when we overlay these data, then ideally what we would like to see is essentially the same shape for these spectra, and the only differences that we can identify would be the noise, which should be different for each measurement because they were measured at a different time. And to a certain extent that's true for these carbon 1s, and also when we overlay the oxygen 1s, to a certain extent that is also true, that the primary difference between these spectra appears to be the noise. When creating a peak model, the first thing we need to do is create a background. So the regions property page allows us to create a background on a spectrum that is displayed in the active tile. So we'll first select a spectrum, and then we know which one of these spectra the background will apply to, and when we press create we then have a background that is calculated for these data based on the background type that has come in as a default. And in this case it's a U3 2GAR background, which makes use of these cross-section fields to calculate a shape beneath the photoemission peaks. Let's have a look at these photoemission peaks in more detail. So let's move away from the regions property page so we don't alter the region limits, and we can look at, by zooming in, the shapes that are created by this particular background type. And as I say, these parameters here determine the shapes that we see in this background. In particular, there is one here that is an offset, and it's currently set to 3. If I set that to 0, and if we observe where this rise in the background occurs, when I enter 0, we can see that the offset starts at where the peak maximum is. So we end up with a shift in where the inelastic scattering is modeled by this 2GAR background based on this offset parameter. And this is important for a polymer in the sense that we would expect there to be a delay before signal is scattered as a result of photoemission electrons scattering with electrons within atoms of the sample in solid state. So here we have the rise in the background of inelastic scattering and a flat background, and this could be significant for a peak model in the sense that the line shapes that we choose would depend on the shapes we see in the background. A more common background to use would be the Shirley background, at least that historically this has been the case. So let's transfer this background as it stands to another spectrum, and then let's alter this background from the 2GAR background to a Shirley. And we can do this by selecting the Shirley background and pressing return. And the first thing we see is the background cannot tolerate the interval that was possible for the 2GAR background. So this is a characteristic of the Shirley background, that it forces a choice of the background limits on the basis of where the background can be calculated in a reasonable way for the data. Now, another characteristic of this Shirley background is that there is a shape that always appears, and it appears beneath the peaks, and it will appear to start wherever there is the most intense peak. So we see here there's a peak at relatively high kinetic energy, and we see an S shape here that may be too early for a polymer of this nature. So if we simply apply a Shirley background to this polymer, we will get shapes beneath the peaks that may influence the line shapes that we choose when we create the peak model as a whole. Now there is another background type that we can choose, which is an offset Shirley background. And the offset Shirley background is dependent on two parameters. The last two parameters in the cross-section field are in the first of these two. If I set that to unity, then we end up with a linear background. If I set this first parameter of the pair to be 0, then I have a Shirley background. And if I use the last of these parameters, or the second of the two parameters that are important to the offset Shirley, and I specify a value that is an offset, just as it was in the case of the U3 2GAR background, and when I press return, we'll see the shape of this Shirley background shift to lower kinetic energy. And this has a result of producing a flat background, which is more physically meaningful for a polymer. So this provides a means of introducing the more popular Shirley background, and also include an interval where the background will be flat. The question of how a background can influence a line shape can be illustrated using this gold spectrum. This is actually part of a survey measurement, but if we apply a background to these data, and we set this to be a linear background, let's put a few points used to fix the background to the data at these limits, and then adjust the background so that what we have here is a straight line that is modeling the extrapolation of the background to higher kinetic energy. So these represent, in some sense, the inelastically scattered electrons with higher kinetic energies than the photoemission peak that we're now trying to consider. Now if we change the background type from linear to a linear Shirley, then what happens is a Shirley background is then calculated based on that linear background that was previously seen. So now I can do a few adjustments here. And ultimately come up with a background that appears to model above and below the peak quite well, with a Shirley shape that takes out some of the inelastically scattered signal. And then if I create a component with a line shape of ds 0, 20, this is a Voigt function, and I say fit, I end up with a reasonable fit to the data that illustrates how this shape in the Shirley is producing a symmetrical shape for a peak that, from the perspective of simply inspection, you might believe had some kind of asymmetry. So this is actually a symmetrical peak. If we choose a different Shirley background, then the line shape that would be needed to fit these data would then have some asymmetry. I can introduce some asymmetry into this DS line shape and say fit. Once again I end up with a good fit. So the type of line shape that I choose for the data is dependent on how I calculate my background shape. The influence of the background on the gold spectrum was much more pronounced than it is for polymethyl methacrylate. Nevertheless, there is some kind of structure here, and it does start to take shape at an offset from the peak, and this offset needs to be modelled, especially when we're looking at the carbon. And if we create the same background that was used for that oxygen 1s, which is an offset Shirley, then we can see, if we zoom in, that the Shirley shape now occurs beneath one of these peaks, and that was not the case with the oxygen, but in the case of carbon the background shape is important, and it is different from simply using a Shirley background applied to polymer data. We will continue the creation of this peak model by going to the Components Property page and introducing a synthetic component. The line shape that has come in is the one that was defined by the element library, and this is not the one that I want to use in this case, so I'm going to select a different line shape, and I'm going to choose a Voigt line shape. This is a Doniuk-Sunjic line shape with an asymmetry parameter set to 0. So this is a Voigt function, and then I'm going to adjust the width of the Gaussian by increasing the value of this second parameter, which is the width of the Gaussian, and then I'm going to adjust the position and the width, and perhaps a little bit more here. And the idea is that I want to position this peak in such a way that it is representative of the CH peak in polymethyl methacrylate. So now we need to add more peaks to represent the other chemical state for carbon within polymethyl methacrylate. So what I'll do is select and then copy the component I've just created. So I paste, and this gives me the same line shape. If I'd created a fresh component, then I would have had to modify the line shape yet again. So by copying it, I use the same line shape as the one I've selected. Now I'll paste, and I'm holding the control key down in order to select the most recently created component when I do the paste operation. And this means I've organized my components in the order in which I've created them in the Components Property page. So now I have a choice. I can try adjusting these peaks to try and make them fit the data better, or simply press the Fit button. Now when optimizing components to the data, the component parameters will be selected on the basis of the initial conditions of this peak model and the sequence of steps that are taken to move these initial conditions to the final solution. And the closer I can make the components to the data before pressing Fit, the better the optimization routine will be able to fit the data in accordance with what I would like to see, namely 2, 1, 1, 1 in terms of the ratio of these peaks. So I'm going to adjust this a little bit more and try and improve my initial conditions before I press the fit button. So having pressed the fit components, I now end up with a solution, and the solution is indicating I have a peak that is 40%, that's this one here, and then I have 3 component peaks, and these all have areas that have been determined by optimization given the line shapes that we've introduced here. Now the ratio of these peaks looks reasonably good in terms of this 40% is about twice the size of this 18% here, indicating that we've got something close to what PMMA would suggest, but it's not quite right. We've got a disparity between these two peaks, and I would expect this one to be closer to the 2-to-1 ratio for these two peaks. So let's optimize again, but this time we'll use a chi-square rather than an RMS. Now if I'm going to use a chi-square, I need to do a few more adjustments. That is to say, I need to adjust the background so that these Lorentzian-like peaks can be accommodated by the difference between the background and the data. So having done that, let's have a look at these peaks and press the use RMS untick, so we'll use a chi-square, and I end up with a new fit, and this time I've got a different range of results. If we add the residual to the display, we can see how well we're doing in terms of data reproduction. This is the residual standard deviation, and for pulse counted data this ought to be about unity, or slightly less than unity when you've got a multiple detector system, which is what has been used to measure these data. So we would expect to have an improvement over what we see here in terms of residual standard deviation. We can also evaluate the data reproduction in terms of this residual itself, that we would look for a uniform distribution about the mean, and that would be an indication that we're producing a good data reproduction across the entire range of these data. So let me do another little adjustment on the basis that I can see there's a slight offset here, so perhaps I need to adjust the background a little bit, and perhaps also this end I can adjust the background a little bit, and then say fit. So we've started to get something close to unity for the residual standard deviation, and the residual itself is looking more uniform, so this is all boding well in terms of data reproduction, but we still need to be sure that the peaks themselves are looking like the ratios we would expect for polymethyl methacrylate, and in this case we can see that we're losing some of the relationships. So the ratio of these two peaks should be 2-to-1, and they're moving apart by virtue of these adjustments I've just made. So let's adjust the line shapes, and we'll make the CC peak more Lorentzian, and perhaps we'll do the same for the CH peak, and then we'll say fit, and perhaps we need to give this a little bit of help in terms of starting the optimization conditions. So when we press the fit, we end up with a different solution based on the initial starting point for these peaks. So now we got more of a relationship that we'd expect. So we have peaks that are about the same intensity here, slightly smaller here, so we could also interpret this as being twice the intensity of these peaks, the average for these peaks anyway. We could also make adjustments on the basis of believing that we have more of a Lorentzian in the double bond O peak, and perhaps we could make the single bond O peak more Gaussian and fit, and ultimately we would like to get a residual that is as close to the data as possible with a uniform distribution. So at this point we might conclude that we have a peak model that is representing polymethyl methacrylate in some sense. So the next step is to gain confidence that this is stable with respect to noise. That is to say, if we measured these data multiple times, how well would this peak model perform when we apply it to data from different measurements? And this is the basis for the Monte Carlo option in CasaXPS. That is to say, the data are simulated and then the fit is applied to the simulated data, and the distribution of the peaks as a function of fitting to different simulations is an indication of the uncertainty that this peak model would introduce into any calculations of binding energy or relative intensities. Monte Carlo calculations are available in two forms in CasaXPS. There's the Test Peak Model button and the Monte Carlo button. These both do the same operation. However, the Test Peak Model button will generate a new VAMAS file that contains a limited number of simulations and models fitted to these simulations, so we can see how the peak model responds visually to the different noise within independent measurements of the same spectrum. The calculation that is performed by the Monte Carlo button allows the calculation of uncertainties in the percent area, and these can be added to the display using annotation on the components property page by ticking the Include Percent Standard Deviation button. So when a table is added to these data, then after Monte Carlo simulation, results from that simulation will appear as part of the annotation. What we'll do initially is to look at the visual feedback by selecting the name field of one of these components, any one of these components, and then by pressing the Test Peak Model button, a simulation will be performed based on this Monte Carlo approach for this peak model, and a new file will be created. So once the simulation is finished, we end up with a column of these carbon monoxide spectra that all represent simulations of the same material measured at a different time, and when we overlay these simulations and look at the peak models that have been fitted to the data, you can see that this peak model based on these Voigt functions for the component line shapes is really very stable, that the variation that we see is limited, and so we should have some confidence that if we were to measure polymethyl methacrylate samples and then apply this peak model, we would be able to measure binding energies and the relative intensities of these peaks based on this particular peak model. So the question is, how does a Voigt function compare against other line shapes that are traditionally used for XPS? I've prepared a file that has these data fitted using two different line shapes. I've got an LA line shape here, and this is actually the same Voigt function. It's just by a different name. The LA line shape will allow asymmetry by introducing two-sided Lorentzian, and it's a generalized Lorentzian, so it doesn't literally always have to be a Lorentzian, and therefore the LA line shape is different from the DS line shape in general, but in the specific of specifying one here, we have a Voigt function. Now the other peak model is based on an SGL line shape. So this is the sum form of the Gaussian-Lorentzian line shape, and it has slight variations in the proportions of the Gaussian and the Lorentzian. The fit is comparable to what we see with the Voigt functions. So when I overlay these two, we can see the residuals are very, very similar, and the position and the starting points for these peaks are all very much the same. So we would expect these to be comparable peak models. However, if we test this SGL line shape peak model against noise, and we'll do this using the Test Peak Model button, then when we overlay these spectra that were fitted using the SGL line shape, you can see that you could not rely on the area or the peak position for either of these correlated peaks, and it has produced a range of different values also for this CO type peak. So although the peak model itself was very stable with respect to a single spectrum, when noise is introduced into the measurement, the SGL line shape has not produced a peak model that could be used without additional constraints added. So let's go back and add a constraint just to illustrate that constraints can be used to improve the reliability of a peak model based on other line shapes and void functions. So if I introduce, for example, a constraint between the full width half maximum of these two peaks, so now the full width half maximum cannot vary independently during optimization for the CH and the CC peak. And if I do the Monte Carlo simulation once again, overlaying the results, we now see stability within the peak model. So with constraints, the SGL line shape does permit a stable peak model with respect to noise. But whenever we include a constraint in a peak model, this represents bias being introduced into the peak model. So we would ideally like to form the best possible line shapes and avoid using constraints if possible, but clearly they are of use if you find that your peak model is unstable with respect to noise.